In the 50 years since the last human footprint was pressed into lunar dust, we decoded the human genome, built the internet, and launched a telescope capable of photographing galaxies that existed when the universe was less than 1% of its current age. Yet the Moon, which sits only 384,000 kilometers away, roughly the distance you would cover if you drove a car without stopping for about 5 months, has been untouched by human hands since December 1972. The question of why is less about rockets and budgets than it is about something far more fundamental. If you want more stories like this one, subscribe and hit the bell. There's a lot more coming. To understand why we stopped going, you first have to understand why we went at all. Because the honest answer is that the Apollo program was less a scientific mission than a political emergency. Dressed up in a spacesuit, it started, as so many crises do, with a sound on the 4th of October, 1957, a small aluminum sphere, roughly the size of a beach ball, lifted off from a remote launch site in Kazakhstan and entered orbit around the Earth, transmitting a simple radio beep that could be picked up by amateur receivers anywhere on the planet. The sphere weighed 83 kilograms, about the same as an average adult human, and it carried no scientific instruments, no cameras, and served no practical purpose beyond proving that it could be done. Its name was Sputnik, which translates loosely from Russian as fellow traveler, and the fact that the Soviet Union had launched it before the United States launched anything at all sent shockwaves through the American political establishment that are difficult to overstate in retrospect. Within days, the New York Times had published 279 articles about a single satellite. The country that had spent the previous decade believing itself to be the unquestioned technological leader of the free world was suddenly confronted with evidence that it might be falling behind. And the fear was amplified by a detail that went largely unstated in the newspapers, but was very well understood in military circles. A rocket capable of putting a satellite into orbit was also, by definition, a rocket capable of delivering a nuclear warhead to any city on Earth. The response was immediate and consequential. Congress passed the National Defense Education Act to flood money into science and engineering programs. NASA was created in 1958, assembled in a matter of months from existing research departments, with a mandate driven by fear rather than curiosity. And still the Soviet Union stayed ahead. In April of 1961, cosmonaut Yuri Gagarin became the first human being to reach space, completing a full orbit of the Earth, while the most the United States had managed at that point was a brief, 15-minute suborbital arc by Alan Shepard 3 weeks later. That gap, between a full orbit and a 15-minute hop, captured the sense of falling behind better than any statistic could. It was in this atmosphere of compounding anxiety that President John F. Kennedy stood before a joint session of Congress on the 25th of May, 1961, and made one of the most consequential promises in the history of technology. He asked for an additional $7 to $9 billion over the next 5 years and declared that the United States should commit itself to landing a man on the Moon and returning him safely to Earth before the end of the decade. The remarkable detail, which tends to get lost in the drama of the announcement, is that at the precise moment Kennedy made this promise, the total combined spaceflight experience of all American astronauts was approximately 15 minutes. The man who would eventually walk on the Moon had disciple. At that point, spent less time in space than it takes to watch a short film. Kennedy himself, in private conversations recorded at the White House, was candid about his actual motivations. In one recording from 1962, he told NASA Administrator James Webb directly that he was not particularly interested in space, that what he cared about was beating the Soviet Union, and that if there was another way to demonstrate American technological superiority, he would gladly do that instead. The Moon mission was chosen specifically because the Soviets did not yet have a significant head start. Unlike Earth orbit, where they had already won, deep space was a race that had not yet begun. Former President Eisenhower, who had overseen the creation of NASA, reportedly called the whole lunar initiative a stunt. He was probably right, in the narrow sense that its primary purpose was symbolic rather than scientific. But it was a stunt that required building the most powerful machine in human history to pull off. And the engineering knowledge generated in the process was genuinely transformative. The Soviet Union, for its part, had its own crewed lunar program running in parallel. Though this was not publicly acknowledged by Moscow at the time, the N-1 rocket, the Soviet equivalent of the Saturn V, attempted 4 launches between 1969 and 1972, and failed catastrophically on all 4 occasions, including one explosion on the launch pad that was, by some measures, the largest non-nuclear explosion in history. The Soviet program was officially acknowledged only after the Cold War ended, and the revelation that the race had been genuinely close, that the Soviet engineers had come within reach of a credible lunar landing capability before their program collapsed, added a layer of contingency to the Apollo story that the triumphalist American narrative had always omitted. The moon landing could have gone differently. The historical accident that it went the way it did, with the United States winning and the Soviet Union concealing its failure, is part of why the program ended when it did. Because a race with a still competitive rival might have had a different political half-life. What followed was the largest peacetime research and development mobilization in American history. At its peak, the Apollo program employed over 400,000 people: engineers, machinists, mathematicians, physicists, technicians, and seamstresses who sewed spacesuit components by hand with tolerances measured in fractions of a millimeter. The budget climbed to 4.4% of the entire federal budget in 1966, which in today's terms would translate to roughly $180 billion per year. To put that in perspective, NASA's current annual budget is approximately $24 billion, which sounds substantial until you realize it represents about 0.35% of federal spending, a drop from 4.4% to a third of 1%, a reduction by a factor of roughly 12. The organizational culture of that era was shaped in ways that are easy to underestimate from the present vantage point. The people who built the Apollo program were, in many cases, engineers in their 20s and early 30s who had grown up during the Depression and the Second World War, and who brought to their work a combination of technical audacity, tolerance for risk, and genuine faith in the power of engineering to solve problems that has few contemporary equivalents in American institutional life. Gene Kranz, the flight director who managed the Apollo 13 crisis, described the culture at Mission Control as one in which failure was genuinely considered unacceptable, not as a motivational slogan, but as a practical engineering standard that shaped every decision about schedule, testing, and risk tolerance. The people who built and flew the Saturn V were operating in an environment where the political stakes were high enough and the funding sufficient enough that they could actually hold themselves to that standard. The decision to end Apollo after 6 successful landings, rather than continuing with missions 17 through 20, which had already been planned and for which hardware was partially built, was made in September of 1970. 2 months before Apollo 13 had even returned its crew safely from the near disaster of an oxygen tank explosion. The remaining 3 missions were cancelled to save approximately $42 million in an overall NASA budget of roughly $3.5 billion, a saving of slightly over 1% of annual spending. The hardware for those missions still exists. 2 complete Saturn V rockets are displayed as outdoor exhibits at the Johnson Space Center and the Kennedy Space Center, exposed to the weather for decades and gradually deteriorating. They are the most powerful machines ever built, and they are lawn ornaments. 6 missions landed successfully on the moon between 1969 and 1972. 12 men walked on the lunar surface. They brought back 382 kilograms of rock and soil, material that scientists are still analyzing today, and still finding new things in. And then, in December of 1972, Gene Cernan climbed back into the lunar module, pulled the hatch closed behind him, and became the last human being to stand on the surface of another world. The program was cancelled not because it had failed, but because it had succeeded. The Soviet Union had been beaten, the political purpose had been served, and the constituency for continuing had evaporated almost overnight. What this means is that Apollo was never the beginning of an era of human space exploration. It was an anomaly, a moment of extraordinary expenditure driven by extraordinary fear, which ended the moment the fear subsided. The 12 people who walked on the moon did so because 2 superpowers were frightened enough of each other to spend whatever it took. And when that fear found other outlets, the money found other uses. Understanding this is essential to understanding everything that came after, because every subsequent attempt to return to the moon has had to operate without that particular fuel, and every subsequent attempt has, in one way or another, failed to find a substitute that was powerful enough and durable enough to see the thing through to completion. The question that now presents itself is whether the combination of forces currently aligned around the lunar South Pole, strategic competition with China, the specific resource value of the ice, the structural embedding of commercial and international partners, is finally sufficient to replace what fear provided in 1961. The history suggests caution. The evidence of the last several years suggests that the conditions are genuinely different from what came before. Both of those things can be true simultaneously. And holding them together, taking the current effort seriously while remaining clear-eyed about the pattern of the preceding 50 years, is probably the most honest way to think about what is coming next. The moon has been waiting for more than half a century. There is a common assumption embedded in the question of why we have not returned to the moon. And that assumption is that returning should be relatively straightforward, that the technology exists, the knowledge was documented, and the main obstacle is simply finding the political will to deploy them again. This assumption turns out to be significantly more complicated than it appears. And the complications begin with what actually happened to the Saturn V rocket after the program ended. The Saturn V remains, more than 50 years after its last flight, the most powerful launch vehicle ever successfully operated, standing 36 stories tall and weighing nearly 3 million kilograms when fully fueled, roughly equivalent to 400 full-grown elephants stacked on top of each other. It could lift 130,000 kilograms to low Earth orbit and send 43,000 kilograms all the way to the moon. Its 5 first-stage engines produced a combined thrust of 33 meganewtons at liftoff, which is enough force to lift a fully loaded aircraft carrier off the ground. When those engines fired during testing at the Stennis Space Center, the sound shattered windows in a bank building 15 miles away. The rocket was built by distributing its components across dozens of contractors. Boeing built the first stage, North American Aviation built the second stage, Douglas Aircraft built the third stage, and IBM built the guidance computer that navigated the whole assembly through space. This division of labor was efficient in the short term and catastrophic for long-term preservation, because while each contractor kept records of their own component, the number of people who understood how all the pieces fit together was always very small. Centered at NASA's Marshall Space Flight Center in Huntsville, Alabama, where Werner von Braun and a team of engineers held the integrated picture in their heads as much as in any document. It is worth pausing on the phrase "in their heads," because it captures something important about the nature of complex engineering knowledge that documentation alone cannot preserve. The Saturn V was not simply a collection of components described in drawings. It was a system whose behavior emerged from the interaction of those components in ways that were, in some cases, only fully understood by the engineers who had watched it fail in tests, made adjustments, and developed an intuitive feel for how the system responded to different conditions. When the program ended and those engineers retired or moved on, the integrated picture went with them. The blueprints survived. But blueprints are only part of what it takes to build something as complex as a Saturn V. The rest is what engineers call tacit knowledge, the understanding that accumulates in the hands and judgment of people who have actually made something work, who know which tolerances matter and which can be fudged, which welds need to be done a particular way, which components were hand-fitted because they could not be manufactured to the required precision and had to be adjusted on the assembly floor. When NASA began looking seriously at rebuilding deep space launch capability in the 1990s, it discovered that some of the manufacturing processes documented in the Saturn V records were no longer physically reproducible because the suppliers no longer existed. The materials had changed, or the machining techniques had been superseded by processes that were different in ways that were subtle but significant. By the 1990s, NASA's own archivists had concluded that maintaining multiple copies of Apollo-era records was unnecessary, and disposed of 2 of their 3 complete sets of documentation. Jeff Bezos, the founder of Amazon, spent money from his personal fortune in the early 2010s to fund an expedition that recovered Saturn V first-stage engines from the floor of the Atlantic Ocean, where they had fallen after separating from their rockets during flight and sinking 2.5 kilometers to the seafloor. The engines had been sitting there for 40 years, and the engineers who examined them were, by their own account, genuinely learning things about how they had been constructed that were no longer in any surviving document. The depth of the knowledge loss becomes clearer when you look at specific components rather than the program as a whole. The ablative material used to coat the Apollo heat shields, a substance called Avcoat, developed by Avco Corporation in the 1960s, was discontinued after the Apollo program ended, because there was no longer any demand for it. When NASA began developing the Orion capsule's heat shield in the early 2010s, engineers discovered that the original AVCOT formulation could not be exactly reproduced, because some of the constituent materials were no longer manufactured. The replacement formulation is functionally similar, but different in ways that required years of testing to characterize, and even after that testing, the heat shield on the Artemis 1 mission behaved differently during re-entry than the models predicted, shedding material through mechanisms that were not fully anticipated. The knowledge embedded in the original Apollo thermal protection system was so thoroughly dispersed over the intervening decades that even with full access to the original documentation, reproducing its behavior required rediscovering things that the engineers of the 1960s had learned by direct experience. The guidance computer is another instructive example of how knowledge disperses. The Apollo guidance computer, designed by Charles Draper's team at MIT, was the most advanced embedded computer in existence at the time of the moon landings. Occupying a volume roughly the size of a large briefcase and capable of performing the navigation calculations required to guide a spacecraft to the lunar surface and back. The software that ran on it, developed by a team that included Margaret Hamilton, whose work on software engineering methodology was foundational for the field, was written in assembly language specific to the AGC's processor architecture, and the expertise required to maintain and modify it was concentrated in a small group of specialists. When the program ended, that expertise dispersed into the broader computer science community, which was rapidly evolving in directions that had nothing to do with lunar navigation. By the 1990s, there were very few people in the world who could read the original AGC software with genuine comprehension. and the institutional knowledge of how the system had been made reliable enough to trust with human lives had largely dissolved into general software engineering practice, losing the specific context that had originally shaped it. Scott Pace, director of the Space Policy Institute at George Washington University and one of the most experienced voices in American space policy, describes the situation with unusual candor. The United States stopped going to the moon and then forgot how. The analogy he reaches for is athletic. Just because you ran a marathon 50 years ago does not mean you can run one today. The muscles have atrophied. The institutional memory has dispersed. And the supply chains that once produced specialized components have reorganized around different markets. Rebuilding the capability is less like starting a car that has been sitting in a garage than like growing an ecosystem that was allowed to go dormant. This is the second layer of the answer to why we have not returned. The stopping itself made returning harder. Every year that passed after 1972 was a year in which the knowledge base eroded a little further. The specialized suppliers moved on, and the gap between where the program ended and where a new program would have to start grew a little wider. The 30-year detour that followed, the space shuttle era, did almost nothing to close that gap, and in some ways made it wider still. The space shuttle flew for the first time on the 12th of April, 1981, exactly 20 years after Yuri Gagarin's first spaceflight. A coincidence that NASA, with its institutional fondness for symbolic dates, was well aware of. The program flew 135 missions over 30 years, carried 355 astronauts from 16 countries, deployed the Hubble Space Telescope, assembled the International Space Station, and demonstrated capabilities in orbit that had never existed before. It was, by the metrics of what it actually did, an impressive machine. What it was not was a vehicle for going anywhere beyond low Earth orbit. The shuttle's operational altitude ranged from roughly 200 to 600 kilometers above the Earth's surface. The Moon is 384,000 kilometers away, roughly 700 times farther than the highest the shuttle ever flew. One observer, writing about the retirement of the shuttle program in 2011, noted with some bitterness that the 5 orbiters had together traveled 537 million miles, completed more than 20,000 orbits around the Earth, and, in a literal sense, never gone anywhere. Every mission began and ended in essentially the same place, circling a planet rather than departing from it. This matters not just as a comment on the shuttle's ambition, but as a statement about what happened to the engineering expertise and institutional culture of human spaceflight during those 30 years. A generation of NASA engineers built careers around the specific challenges of low Earth orbit: thermal protection systems for re-entry, docking mechanisms for the space station, the logistics of moving large payloads between orbiter and payload bay. These were genuinely difficult problems, and solving them generated real knowledge. But none of it was knowledge about how to send humans beyond the Moon's orbit, how to protect them from deep space radiation for months at a time, or how to design life support systems capable of operating in isolation from Earth resupply for extended periods. The muscles required for deep space exploration were the ones that went unexercised for 3 decades. A useful comparison is what happened to the American shipbuilding industry in the decades after the Second World War. The massive capacity built up during the war atrophied as demand shifted. The workers who had built Liberty ships retired without training successors, and by the 1980s, the institutional knowledge required to build large naval vessels quickly had largely dispersed into history. Rebuilding it required time, investment, and the rediscovery of techniques that had once been common knowledge. The parallel with NASA's deep space capability is imperfect but instructive capability that is allowed to go unused long enough eventually has to be rebuilt from near scratch. And rebuilding it is always more expensive and time-consuming than maintaining it would have been. The financial picture reinforced the problem. The shuttle cost approximately $450 million per launch, considerably more than the original projections, which had promised a routine, airline-like operation at a fraction of that price. The program's total cost over its operational life, adjusted for inflation, was $196 billion. NASA's overall budget, meanwhile, had settled into a range below 1% of federal spending and was staying there, with the shuttle consuming roughly 30% of NASA's annual budget just for operations, and the International Space Station consuming much of the rest. The agency was in the position of a household that has committed most of its income to mortgage and utility payments, with very little left over for anything else. The ambition of reaching the moon again, let alone Mars, was structurally crowded out by the cost of maintaining what already existed. The Challenger disaster of 1986 and the Columbia disaster of 2003 each imposed their own costs on the program, not merely in the lives of the 14 astronauts who died in those two accidents, but in the years of flights suspended during accident investigations, in the redesigns and additional safety measures that compressed the operational calendar, and in the erosion of the public and political confidence that any program depends on for its continued funding. After Columbia, NASA spent 2.5 years grounded, and when flights resumed, the program was already past the midpoint of its operational life, with no clear successor in place. The one moment during the shuttle era when a serious attempt was made to look beyond low Earth orbit came in 1989, when President George H.W. Bush announced the Space Exploration Initiative, a proposal to return humans to the moon and eventually send them to Mars. NASA's response was to produce a plan that would require $500 billion over 20 to 30 years. Congress, faced with that number and a budget deficit that was already a source of political anxiety, declined to fund it. The initiative died without producing a single flight, leaving behind only the memory of an ambition that briefly surfaced and then submerged again. There is a structural tension at the heart of human space exploration that has no clean solution, and understanding it requires holding two timescales in your head at once: developing the capability to establish a sustained human presence beyond Earth orbit, building the rockets, the habitats, the life support systems, the supply chains, training the people, developing the operational procedures. Takes somewhere between 20 and 30 years from the decision to begin to the point where the capability actually exists. Presidential terms last 4 years, with a maximum of 8. Congressional election cycles run on 2-year intervals. The result is a mismatch between the timescale on which technology matures and the timescale on which political priorities change. And the history of American space policy since 1972 is essentially the story of that mismatch playing out in slow motion. Over and over again, the Constellation program, announced by President George W. Bush in January 2004 following the Columbia shuttle disaster, is the clearest illustration of how this works. The program proposed to develop a new family of rockets called Ares and a new spacecraft called Orion, with the goal of returning astronauts to the moon by 2020 and eventually sending humans to Mars. By the time Barack Obama took office in January 2009, Constellation had been running for 5 years and had consumed approximately $9 billion. An independent review panel, convened at the Obama administration's request and chaired by former Lockheed Martin CEO Norman Augustine, concluded that the program was so far behind schedule and so severely underfunded that it could not achieve its goals without an additional $3 billion per year, money the administration was unwilling to allocate. In February 2010, the program was cancelled. The cancellation was met with a response that conveyed the weight of what was being discarded. Neil Armstrong, Gene Cernan, and Jim Lovell, the first man on the moon, the last man on the moon, and the commander of Apollo 13, wrote a joint open letter condemning the decision in terms that were unusually direct for men of their generation and temperament. They argued that the United States was on the verge of becoming a second-rate, spacefaring nation, that the investment already made in Constellation was being thrown away, and that the gap resulting from the end of the shuttle and the absence of any American deep space capability would be damaging in ways that would take decades to repair. The letter was ignored. The pattern repeats with such consistency that it has become something like a structural feature of American space policy rather than a series of individual failures. Richard Nixon ended Apollo and replaced it with the shuttle. Ronald Reagan reduced the shuttle's ambition and directed resources toward building a space station. George H. W. Bush proposed going back to the moon and Mars, received no funding, and watched the initiative collapse. George W. Bush proposed returning to the moon through Constellation. Barack Obama cancelled Constellation and replaced it with a Mars aspiration so distant as to be, in any practical political sense, meaningless. Donald Trump revived the lunar focus under the name Artemis. Each transition consumed years of work and billions of dollars while producing movement in a different direction from the one before. There is a further dimension to this problem that tends to get overlooked in discussions that focus on presidents and their priorities. Congress. Even when a president is genuinely committed to a lunar program and willing to defend it politically, the program must still survive the annual appropriations process, in which a different set of political actors with different constituencies, different committee assignments, and different ideas about what the federal government should be spending money on, decide how much of the president's request will actually be funded. NASA's experience with Constellation is illustrative. The program was not simply cancelled by Obama on a whim, but had been chronically underfunded by Congress throughout its life, receiving roughly 75 to 80% of what it requested in most years, which forced program managers to continually defer development work and extend timelines in ways that ultimately made the Augustine Commission's conclusion that the program was unexecutable. A self-fulfilling prophecy. The geography of the congressional problem is also worth understanding. NASA's major facilities are distributed across multiple states. The Marshall Space Flight Center in Alabama, the Johnson Space Center in Texas, the Kennedy Space Center in Florida, the Jet Propulsion Laboratory in California, and the contractors who build NASA hardware are similarly distributed, with major work packages flowing to companies in dozens of states. This distribution means that any major change to a NASA program affects employment in multiple congressional districts, which creates a political constituency for the status quo that is separate from any genuine assessment of whether the program is working. The Space Launch System, which the Inspector General has described as too expensive to be sustainable, survived multiple attempts to shift its budget toward alternative commercial rockets, in part because the manufacturing work is distributed across states with significant congressional representation. The program is, in a sense, protected by its own inefficiency. The very features that make it expensive are the features that give it political durability. A survey conducted in 2018 found that Americans, when asked to estimate NASA's share of the federal budget, guessed an average of 6.4%, when the actual figure was approximately 0.5%. 85% of respondents said they believed NASA's budget should be increased, while simultaneously overestimating it by a factor of roughly 12. The gap between public perception and fiscal reality is its own kind of structural problem. There is genuine popular support for ambitious space exploration, but that support is not calibrated to what ambitious space exploration actually costs. And when the true figures become politically visible, the support tends to erode. China's space program, by contrast, operates under a 5-year planning system that does not reset with elections. The targets set in one planning period carry into the next. The engineers who design a rocket in 2020 are still working on the same rocket in 2025. And the institutional knowledge accumulated in one program carries directly into the next. This is not an argument that the Chinese political system is preferable. It comes with very different and serious costs. But it is an accurate description of why a program structured that way is better suited to the specific challenge of long-duration space infrastructure development than one that resets priorities every 4 to 8 years. Here is the detail that changes the texture of the current moment, and that distinguishes what is happening now from every previous attempt to return to the moon since 1972 China has, with remarkable consistency and relatively little fanfare, been executing one of the most methodical lunar exploration programs in history, the Chang'e program, named after the Chinese goddess of the moon. Began with an orbiter in 2007 and has proceeded in careful incremental steps ever since. Chang'e 3 landed a rover on the near side of the moon in 2013, becoming the first soft lunar landing since the Soviet Lunar 24 mission in 1976. Chang'e 4, in January 2019, landed on the far side of the moon, something that had never been done by any space agency in history, requiring the prior deployment of a relay satellite to maintain communications across the lunar limb. The Yutu-2 rover deployed from that mission was still operating as of 2024, more than 5 years after landing, becoming one of the longest operating lunar rovers ever built. Chang'e 5 returned samples from the near side in 2020. Chang'e 6, in June 2024, returned samples from the far side. Another historical first, since all previous lunar sample returns had come from the same near-side terrain that Apollo had explored. The mission required a landing, sample collection, an ascent from the lunar surface, autonomous rendezvous and docking with an orbiter in lunar orbit, and a return journey to Earth. A chain of operations of considerable complexity, executed successfully on the first attempt. China's record in lunar exploration stands at 4 attempted landings and 4 successes. The declared ambition does not stop there. Chang'e 7, expected to launch in 2026, will explore the lunar South Pole in detail, specifically looking for the water ice that radar data has suggested lies in permanently shadowed craters. Chang'e 8, planned for 2028, will test the extraction and processing of lunar resources in preparation for a crewed outpost, and the official target, stated by Chinese space officials at a conference in July 2023, is to land taikonauts on the moon before 2030, with a crewed research station at the South Pole operational by the early 2030s. What makes the Chinese program's progress particularly striking is not just the results but the method. Each mission has been designed as a building block for the next, with technologies tested on one mission reused and extended on the following one, and with failure treated as information rather than occasion for program cancellation. The contrast with the American pattern of the previous 50 years, in which programs were cancelled when they encountered difficulty, their partially developed components either abandoned or repurposed into successor programs with different goals, is structural rather than merely organizational. A program that is allowed to learn from its failures and continue is a fundamentally different kind of enterprise from one that is subject to termination whenever its cost or schedule deviates from the original projection. NASA Administrator Bill Nelson, in an interview with Politico, put it simply, it is a fact that the two nations are in a space race. The framing is notable because for years the official NASA position was that Artemis was a scientific program operating on a timeline determined by technical readiness rather than competitive pressure. The acknowledgement that the competitive dimension is real reflects a change in the political atmosphere that has become increasingly difficult to ignore. The competitive dynamic is sharpened by a specific legal and regulatory context that most coverage tends to underemphasize. The Outer Space Treaty of 1967, which the United States, the Soviet Union, and most other spacefaring nations signed at the height of the original space race, prohibits any nation from claiming sovereignty over the Moon or any other celestial body. The Moon belongs, in the language of the treaty, to all of humanity, which sounds like a reassuring constraint until you examine what it does and does not cover. The treaty prohibits territorial claims, but says relatively little about the extraction and use of resources. And the question of who has the right to mine water ice from a permanently shadowed crater at the lunar South Pole is one that international space law has not yet answered in any binding way. The United States passed the Commercial Space Launch Competitiveness Act in 2015, which explicitly grants American citizens and companies the right to own resources they extract from celestial bodies. China has articulated its own framework for resource rights. The legal architecture for adjudicating competing claims over the same deposit of water ice in the same crater at the lunar South Pole does not exist. And the two programs most likely to place humans in that vicinity within the next decade have incompatible frameworks for thinking about who those resources belong to. Both programs are targeting the same location, the lunar South Pole, and specifically, the permanently shadowed craters where water ice is thought to exist in substantial quantities. The area around Shackleton Crater, near the South Pole, is described by space planners on both sides as prime real estate, a phrase that, in this context, is more literal than it might initially sound. In October of 2009, NASA deliberately crashed a rocket into the Moon. The target was a crater called Cabeus, near the lunar South Pole, chosen because it lies in permanent shadow, a region so deep and so sheltered by the surrounding terrain that sunlight has never reached its floor, possibly for billions of years. The rocket's upper stage, weighing 2.2 metric tons and traveling at 9,000 kilometers per hour, fast enough to cross the continental United States in roughly 25 minutes, struck the crater floor and excavated a plume of material that rose above the crater rim and was briefly exposed to sunlight. A following spacecraft flew through the plume, analyzed its composition, and transmitted the data back to Earth before it too impacted the surface. The analysis found water. Specifically, it found a water concentration of approximately 5.6% by mass in the excavated material, including, in some areas, what appeared to be nearly pure ice crystals rather than water molecules mixed into the soil. This was confirmation of what orbital radar data had been suggesting for more than a decade, and it settled a debate that had been running in planetary science since the 1990s. When the Clementine satellite first returned data from the lunar poles that was consistent with the presence of ice but too ambiguous to be conclusive, the permanently shadowed craters near the lunar poles contain water ice that has been accumulating and preserved for potentially billions of years, delivered by the comets and asteroids that have struck the Moon throughout its history and protected from evaporation by temperatures that, in the deepest parts of the shadowed craters, hover around -198 degrees Celsius. Cold enough to preserve volatile compounds indefinitely, the total estimated mass of water ice at the lunar poles, based on data from multiple missions including the Lunar Reconnaissance Orbiter and India's Chandrayaan-1 spacecraft, is approximately 600 billion kilograms. To make that number feel real, 600 billion kilograms is enough to fill at least 240,000 Olympic-sized swimming pools. And this is a conservative estimate, bounded by the sensitivity of the radar instruments that took the measurements. Deeper penetrating instruments would almost certainly find more, The significance of this ice extends well beyond its value as drinking water. Though drinking water is genuinely valuable on a world that has to import everything it uses from Earth at a cost of tens of thousands of dollars per kilogram, water molecules can be split by electricity into hydrogen and oxygen, two gases with obvious uses for a lunar base. One as breathable atmosphere and the other as the most effective rocket propellant available to current technology. A base that can produce its own rocket propellant from local resources does not need to carry fuel all the way from Earth for every mission it launches. It becomes, in the language of space planners, a node rather than an endpoint. The Moon stops being a destination and starts being a platform, a place from which further missions into the solar system can be staged at dramatically lower cost. This is the concept that engineers and planetary scientists refer to as in situ resource utilization, using what is already present at a destination, rather than transporting everything from Earth. Every Apollo mission carried everything it needed from home: food, water, oxygen, fuel, equipment. This was feasible for 3-day visits at enormous expense. But it becomes unsustainable as the duration and frequency of missions increase. The cost of launching 1 kilogram of material from Earth's surface to the lunar surface runs to tens of thousands of dollars depending on the launch vehicle and mission profile. A lunar base that imports all of its consumables from Earth is a base whose operating cost grows linearly with both the size of the base and the length of its operation. A financial structure that has no path to sustainability. A base that can produce its own water, oxygen, and propellant from local ice breaks that dependency for the most critical and most massive consumables, and transforms the economics of everything that comes after it. In the longer term, a lunar propellant depot could service missions to Mars, to the asteroid belt, and to the outer solar system, reducing the cost and increasing the payload capacity of every mission that passes through it. Paul Spudis, one of the planetary scientists who spent decades analyzing lunar polar data, described the lunar South Pole as potentially the most valuable piece of real estate in the solar system. And the logic behind that description is sound. Whoever establishes the infrastructure to extract and process that ice first will have a significant and lasting advantage in the economics of space exploration. And the 600 billion kilograms of ice estimated to exist at the lunar poles is, under this framework, a strategic resource of the first order. The Apollo missions, in the context of everything discussed so far, look different once you understand what they were and were not. They were extraordinary feats of engineering, planning, and human courage. But they were also, from a logistical standpoint, camping trips. The longest any Apollo crew spent on the lunar surface was just under 75 hours, a little over 3 days. During that time, they lived and worked within the constraints of what they had brought with them, and returned to Earth before those constraints became limiting. The ambition of Artemis and of the parallel Chinese program is fundamentally different. The goal is to establish a sustained human presence, people who stay on the Moon for weeks or months at a time, working, conducting science, building infrastructure, and the transition from visiting to staying introduces a category of challenges that Apollo did not need to solve. Challenges that turn out to be considerably more difficult than they might initially appear. The first of these is lunar dust, a material that is, in the assessment of engineers who have studied it carefully, one of the most hostile substances that any technology has had to contend with. Lunar regolith is produced by billions of years of meteorite impacts on a surface with no atmosphere to weather it, no water to smooth its edges, no biological activity to break it down. The result is a powder composed of particles with edges as sharp as broken glass. Particles that are also electrostatically charged by exposure to solar radiation. and therefore cling to any surface they contact with a tenacity that ordinary cleaning cannot overcome. During the Apollo missions, the dust-coated spacesuits, clogged mechanical joints, scratched visors, and found its way into equipment through gaps that were not supposed to exist. Apollo 17 astronaut Harrison Schmitt, the only professional geologist to walk on the moon, and the last human to leave the lunar surface, developed what he described as lunar hay fever within an hour of entering the module after the first EVA, with symptoms that persisted throughout the mission. The dust the crew tracked in on their suits had become airborne inside the cabin and was being inhaled. And while the short duration of the Apollo missions meant this was a tolerable inconvenience rather than a serious health risk, a crew member spending 30 days in a lunar habitat would face a genuinely different exposure calculation. After 3 EVAs, 3 excursions outside the lunar module, the suit bearings on some Apollo missions were so contaminated that engineers estimated a 4th excursion would have been impossible. For a base that expects its inhabitants to venture outside regularly for weeks at a time, this is a problem that requires a solution that Apollo never had to develop. NASA's Lunar Dust Mitigation Roadmap, published in the autumn of 2024, describes the range of technologies currently under development: electric fields that repel dust from solar panels and camera lenses, specialized coatings that reduce adhesion, pneumatic collection systems, cleaning protocols for airlocks. The word roadmap is significant. It acknowledges that the solutions are still in development, and that solving the dust problem is a prerequisite for any long-duration surface presence. The second challenge is radiation. The moon has no magnetic field and no atmosphere thick enough to absorb energetic particles from the sun or from cosmic rays originating elsewhere in the galaxy. The Earth's magnetic field, which deflects most of this radiation before it reaches the surface, extends far enough into space to provide some protection for low Earth orbit missions. The International Space Station operates within a region where the field provides meaningful shielding. Beyond a distance of roughly 60,000 kilometers from Earth, that shielding is gone, and the lunar surface receives the full unfiltered flux of space radiation. For a 3-day Apollo mission, the accumulated dose was within acceptable limits. For a 30-day Artemis surface stay, the calculation is entirely different. And for a permanent outpost measured in years, radiation protection becomes one of the central engineering problems of the entire enterprise. The types of radiation involved are worth distinguishing because they present different challenges. Solar particle events, eruptions from the sun that can occur with little warning and deliver high doses of radiation over hours or days, can be managed by designing shielded refuges within the habitat where crew members can shelter during an event. Galactic cosmic rays are a more persistent problem. High-energy particles originating from outside the solar system that pass through almost any material currently practical to build with, accumulating in the body over time and increasing cancer risk with every day of exposure. The only reliable mitigation is mass. Thick walls of material between the radiation source and the crew, and the most mass-efficient material for this purpose, as it happens, is regolith. Building underground or under a thick layer of compacted lunar soil addresses both the radiation problem and the thermal problem simultaneously, which is why the baseline habitat design for both the American and Chinese programs involves placing the primary living and working spaces below or within the surface, rather than in pressurized modules sitting exposed on the regolith. The current leading approach involves construction robots capable of excavating, transporting, and compacting regolith in a useful configuration, capability that does not yet exist at operational scale. Though prototype systems are under active development, the third challenge is the lunar thermal cycle. The moon rotates slowly, completing one rotation every 29.5 Earth days. which means that any given point on the surface experiences about 14.5 Earth days of continuous sunlight, followed by 14.5 Earth days of continuous darkness. The temperature swings between these two states are extraordinary. The sunlit surface reaches approximately 127 degrees Celsius, while the shadowed surface drops to approximately minus 183 degrees Celsius, a difference of 310 degrees, cycling every 29 days. This imposes thermal stresses on any structure or mechanism that must survive it, and makes solar power intermittent in ways that complicate the design of any energy system that needs to operate continuously. The solution being most actively pursued involves placing habitats and infrastructure on crater rims near the South Pole, where certain elevated locations receive near-continuous sunlight due to the low angle of the sun above the lunar horizon. The rim of Shackleton crater has points that are illuminated for more than 80% of the year, providing a relatively stable solar power supply while maintaining close proximity to the permanently shadowed interior where the ice deposits are located. It is, by an accident of lunar geometry, an almost ideal location for the first human outpost beyond Earth, which is precisely why both the American and Chinese programs have identified it as their target. There is also a psychological dimension to long-duration lunar habitation that deserves acknowledgement. A crew member at a lunar South Pole outpost in the 2030s, committed to a 30 or 60-day rotation, faces a different kind of challenge from anything Apollo required: genuine isolation from Earth's social fabric, confined quarters, limited natural light, high-stakes work in an environment that is hostile in multiple simultaneous ways, and the specific stress of knowing that any serious equipment failure may be beyond the reach of rapid rescue. The human performance research conducted on analog environments, Antarctic winter overstations, long-duration International Space Station missions, isolation studies conducted in Hawaii and Moscow, has generated useful data, but the lunar surface introduces variables that have no direct analog, and the design of the habitat environment, the work schedule, the communication protocols, and the crew selection process will all need to account for factors that Apollo never had to consider. The cumulative weight of these challenges, dust, radiation, thermal extremes, power supply, psychological stress, is a description of why the transition from the Apollo model of brief visits to the Artemis model of sustained presence is a genuinely different category of undertaking, one that required developing entire new fields of engineering that did not exist when CERN climbed back into the lunar module in December of 1972. The gap between visiting and staying is one of kind rather than scale. The Artemis program, which is the current American effort to return humans to the moon, was formally organized under the Trump administration in 2017, building on the rocket and spacecraft components that had survived from the Constellation program. The Orion capsule, which had been kept alive as a crew return vehicle for the space station, and the Space Launch System, which was developed from shuttle-derived components under the NASA Authorization Act of 2010. The program was given a target date of 2024 for the first human landing, a timeline that was widely understood within the space community to be politically driven rather than technically realistic. From 2012, when serious development of Artemis-related systems began under various program names, through 2025, the program consumed an estimated $93 billion. Each launch of the Space Launch System rocket is estimated to cost $4.1 billion, a figure that NASA's own Inspector General described as unsustainable, and that exceeds, adjusted for inflation, the cost of the Saturn V launches that sent Apollo crews to the moon. The Orion capsule that returned from the first uncrewed test flight in late 2022 was found to have a heat shield that had degraded in ways that engineers had not predicted, shedding material during re-entry through mechanisms that were not fully understood, and requiring changes to the planned re-entry trajectory for future crewed flights. Artemis 2, the first crewed mission, which will carry 4 astronauts on a 10-day arc around the Moon without landing. Similar in profile to Apollo 8's circumlunar mission in 1968, was originally targeted for 2024, then delayed to September 2025, then to February 2026, then to March 2026. In February of 2026, with the rocket already assembled on the launch pad and the crew in quarantine, engineers discovered an issue with the helium system in the rocket's upper stage, a component that was behaving differently from what the data indicated it should, and the vehicle was rolled back to the vehicle assembly building for repairs, with the next launch window targeting April of 2026. Artemis 3, which would be the first crewed landing, is currently planned for mid-2027. The pattern of delays is frustrating, and the costs are genuinely difficult to justify in isolation. But the more useful comparison is not between Artemis and Apollo, 2 programs operating in entirely different political and technological contexts, but between Artemis and what it is actually trying to accomplish, which is the first phase of a sustained human presence rather than a flag and footprints visit, measured against that ambition. The challenges are proportionate, even if the management of them has sometimes been less than optimal. A useful reference point is the development cost of the International Space Station, which consumed approximately $150 billion over roughly 20 years to produce a facility that has been continuously occupied since November 2000, hosted over 260 people from 20 countries, and generated research that would have been impossible to conduct on Earth, evaluated against what it actually is: a permanently staffed outpost in an environment completely hostile to human life. The space station looks like a reasonable investment, even if the per-kilogram cost of getting people and supplies there remains, by any ordinary standard, absurd. The lunar South Pole outpost that Artemis is working toward will face the same evaluative tension. The costs will look unreasonable, measured against terrestrial alternatives. And they will look like an inevitable investment, measured against the strategic and scientific value of what they are purchasing. Which frame you apply to the numbers is, in the end, a question about what you believe the Moon is worth. The most significant structural difference between the current moment and every previous attempt to return to the Moon since 1972 is a change in who is involved. And that change makes the enterprise substantially more resilient to the political disruption that has derailed every previous effort. By January of 2026, 61 countries had signed the Artemis Accords, a set of principles for cooperative space exploration developed by NASA and the United States Department of State in 2020. The signatories include traditional American allies like Japan, Canada, Australia, and most of Western Europe, but also India, Brazil, South Korea, and a growing number of countries from Africa and Southeast Asia. Japan has negotiated a specific commitment in exchange for providing a pressurized lunar rover capable of carrying 2 astronauts for up to 30 days outside the habitat. Japanese astronauts will be included among the crews of future Artemis landing missions, making them the first non-Americans to walk on the Moon's surface. Canada is contributing Canadarm3, a next-generation robotic arm for the Lunar Gateway space station that will orbit the Moon as a staging point for surface missions. The European Space Agency is building the Gateway's habitation module and the service module for the Orion spacecraft. These contributions are significant beyond their technical value. When Canada has committed engineering resources and political capital to building hardware that only makes sense in the context of a functioning lunar program, the incentive structure for maintaining that program across political transitions is different from what it was when the program was entirely an American undertaking. Cancelling Artemis would mean cancelling commitments to allied governments, disrupting bilateral relationships that extend well beyond space policy, and absorbing costs associated with breaking contracts with partner agencies. The political cost of cancellation has been deliberately raised by building the architecture of partnership into the program from the outset. The private sector dimension is equally significant. SpaceX, under a contract worth approximately $2.9 billion, is developing the Starship human landing system that will carry Artemis crews from lunar orbit to the surface. An adaptation of the same Starship vehicle that the company is also developing for its own commercial purposes, including eventual missions to Mars. Blue Origin, founded by Jeff Bezos, holds a contract to provide an alternative lander for later Artemis missions. Both companies have invested their own capital in the development of these systems, because both companies see a commercial future in lunar transportation that extends beyond the NASA contract. SpaceX in particular has made its long-term ambitions explicit. The Starship program is designed to make humanity multiplanetary, beginning with the Moon and continuing to Mars. And the company has structured its development work around that goal in ways that do not depend on any single government contract remaining in place. The implication of this is significant and historically unusual for the first time since Apollo. There is a private actor with sufficient capitalization, technical credibility, and stated commercial interest in the lunar surface to develop hardware for reasons that are, at least partly, independent of the political cycle. When a company with SpaceX's capitalization and strategic clarity has committed its own resources to lunar lander development, resources that are not contingent on the annual congressional appropriations process, the program has an anchor that did not exist in any previous iteration of the lunar return effort. The program can survive a change in presidential administration in a way that Constellation could not, because the commercial commitments and international partnerships create a fabric of obligation and interest that is genuinely difficult to unilaterally dissolve. The Chinese program, meanwhile, is constructing its own parallel architecture, the International Lunar Research Station, a competing framework to the Artemis Accords that China has organized with Russia and a growing list of partner nations. Currently has 13 member states and is targeting the same South Polar region. The presence of two serious, well-resourced programs with overlapping targets creates a competitive dynamic that, however uncomfortable it may be in geopolitical terms, functions as a structural guarantee that at least one of them will follow through. What is perhaps most significant about the current architecture, on both sides, is that it represents a genuine departure from the model that produced Apollo and then allowed it to end. Apollo was a bilateral competition between two governments, and when one of those governments decided it had won, the competition was over. There was no mechanism by which the decision to stop could be resisted by any actor other than the political leadership that made it. The current landscape involves commercial companies with independent balance sheets, international partner agencies with their own legislative mandates, and national programs on two sides of a geopolitical rivalry, all of whom have made commitments that are interconnected in ways that create genuine friction against any single actor deciding to withdraw. This is not a guarantee that the programs will succeed. The history reviewed throughout this conversation is a catalogue of programs that failed despite having institutional support. But it is a meaningful structural difference from everything that preceded it. And it is the primary reason why the current moment deserves to be taken more seriously than the long series of false starts that preceded it. The question that opened this documentary, why has no one returned to the moon in more than 50 years, has by now accumulated a layered answer. Apollo was an anomaly, a product of fear rather than sustained ambition. And when the fear ended, the program ended with it. The stopping itself eroded the knowledge and infrastructure that would have made returning easier. 30 years of low Earth orbit operations allowed the capability for deep space human flight to atrophy, quietly and largely without notice. While engineers built excellent careers, solving problems that had nothing to do with leaving Earth orbit. The mismatch between the timescale of space program development and the timescale of democratic politics produced a cycle of initiation and cancellation that consumed billions of dollars and decades of potential progress without producing a single flight beyond Earth orbit after 1972. And when the technical requirements for actually staying on the moon, rather than visiting it briefly, became clear, the engineering challenges turned out to be substantially more complex than a casual reading of the Apollo record would suggest. But something has shifted in the structure of the current effort that makes the present moment different from all the previous ones. The combination of international commitments that carry genuine political weight, private sector investment driven by commercial logic rather than political goodwill, and the specific competitive pressure created by China's methodical progress toward the South Pole has created conditions in which the program is more resilient to disruption than any of its predecessors. The first crewed flyby of the moon since 1972 is expected to happen in the spring of 2026. Assuming the helium system repair completes successfully, the first crewed landing since 1972 is planned for mid-2027. The first Japanese astronaut on the lunar surface is expected sometime in the late 2020s or early 2030s. The first permanent outpost, the thing that Apollo never even attempted to be, is targeted for the early 2030s on the American side, and the same decade on the Chinese side. There is also a larger frame within which the question of returning to the moon sits, one that the day-to-day coverage of launch delays and budget overruns tends to obscure. The 12 people who walked on the moon between 1969 and 1972 represent the full extent of human presence beyond Earth in the entirety of our species' history. 4.5 billion years of biological evolution, 10,000 years of recorded civilization, 500 years of scientific inquiry, and the sum total of it all is 12 people. On 12 occasions, for a combined total of roughly 80 hours on the surface of another world. Every other place in the universe that we have visited with machines, with orbiters and landers and rovers and probes, instruments of extraordinary sophistication that have collectively taught us an enormous amount about the solar system we inhabit, but that have done so without the presence of a living mind to experience what they found. The Voyager probes have traveled beyond the boundary of the solar system and are still transmitting more than 47 years after launch. The Perseverance rover is drilling rock cores on Mars and photographing landscapes that no human eye has ever seen directly. The James Webb Space Telescope is returning images of galaxies that formed before the Milky Way had finished assembling itself. All of this is extraordinary, and none of it involved a human being actually being present. The ambition of what is being attempted now, however slowly, however expensively, however imperfectly managed, is to change that ratio, to make the 12 people and the 80 hours the beginning of something rather than the entirety of it. The moon is, in this sense, the test case for a larger question whether human beings are actually going to become a spacefaring species in any meaningful sense of that phrase, or whether the trajectory of the last 50 years, impressive machines, absent people, is the permanent condition of our relationship with space. The answer is genuinely open. Whether all of this proceeds on schedule is, given the history reviewed here, a question that deserves significant skepticism. Space programs are complex, expensive, and prone to exactly the kinds of surprises. a heat shield that degrades in unexpected ways, a helium system that misbehaves on the launch pad, that compress schedules and inflate costs. The $93 billion already spent has bought a program that has successfully launched one uncrewed mission and has yet to put a single person beyond low Earth orbit. The next several years will determine whether the structural changes that make this attempt different from its predecessors are sufficient to overcome the structural challenges that have blocked every previous attempt. But the structural conditions have shifted in ways that are genuinely different from anything that existed in 1972, or 1989, or 2004. The combination of international commitment, private investment, and competitive pressure that now surrounds the lunar return effort means that the probability of another 50-year gap is lower than at any point since Apollo ended. And the specific resource waiting at the South Pole gives this race a concrete, strategic dimension that the original space race, for all its intensity, never quite had. The Apollo astronauts went to the moon to prove a political point. The people who go next will go because the ice in those craters, and what it represents for the economics of everything beyond it, is genuinely worth having. That is a different kind of motivation, and it may prove more durable than fear. The moon has been waiting 384,000 kilometers away, undisturbed since December 1972. The dust that 12 human beings pressed their boots into is still there, finer than talcum powder, sharp as broken glass, carrying the exact impressions of every step because there is no wind to erase them and no rain to wash them smooth. The footprints of Neil Armstrong, Buzz Aldrin, Pete Conrad, Alan Bean, Alan Shepard, Edgar Mitchell, David Scott, James Irwin, John Young, Charles Duke, Gene Cernan, and Harrison Schmitt are preserved with the fidelity of a casting mold, exactly as they were left, waiting for the next visitor with the same patience that the moon has applied to everything else in its 4.5 billion years of existence. Somewhere near the South Pole, in craters that have been dark for longer than complex life has existed on Earth, water ice that arrived on comets billions of years ago lies frozen and preserved, waiting for the chemistry of a living world to find it useful. The technology to reach it exists. The motivation, for the first time since 1972, is real and structural rather than contingent on the political mood of a single government. The gap between where we have been and where the evidence suggests we are capable of going is, finally, beginning to close. And the next footprints, whenever they come, will be pressed into a surface that has been waiting for them for more than half a century. It took a decade to get there the first time. It has taken more than 50 years to find the conditions to try again. What happens next will depend on whether those conditions hold, and on whether the people and institutions now committed to making it happen have the patience and resilience that the political systems around them have, historically, found very difficult to sustain.